Alright, so the next thing we are going to see is given a binary tree of some arbitrary structure like this, how to convert that to a binary search tree by preserving the structure of the tree. So what I mean is this. So here you have a binary tree with some data for the nodes. Now this binary tree is not necessarily a binary search tree. As we can see, the internal node data is 19. It is less than its left child. So that's not the way a binary search tree should be, right? So the data for our internal node should be greater than or equal to its left child. So that itself rules out this to be a binary search tree. So it's just a binary tree. So now what we want to do is we want to convert this to a binary search tree such that the structure, means like the way the nodes are organized, is kind of retained. Okay, so that's what we want to do. And we are going to make use of the property that we just went through, that the in-order traversal of a binary search tree will list the nodes of the tree in a sorted order. So what we are going to do is this. So given this binary tree, we'll first do an in-order traversal of this binary tree. So the way we'll do the in-order traversal of this binary tree is start with the root. Again, don't print the root, go to the left, don't print the root, go to the left further. So node 3 is the left child, you cannot go further down, so node 3 and the data 22, then node 1 and the data 27. Then go to the right subtree, there's no left child, so print the root of the subtree, so 4 and the data 13, then 5 and the data is 18. So go to the root, which is 0 and the data is 19, and then print the right subtree, which is 2 and 14. So this is the in-order traversal of this binary tree, and these are the data accordingly, right? So now what we'll do is we will sort just the data here. So we will just leave the index of the nodes as it is and just sort the data. So if you sort the data, it is like what, 13, then followed by 14, 18, 19, 22 and 27. So these are the index values of the nodes, and this is the sorted order of the data. So what we are going to do is we are going to just superimpose on these nodes the data which is now in the sorted order. So for node 3, the data is now going to be 13. For node 1, the data is going to be 14. For node 4, the data is going to be 18. For node 5, the data is going to be 19, 0, 22 to 27. So we just superimpose. So what is the data for those nodes? Just replace them with the data in sorted order. So how did we do this? Given a binary tree with the data, do an in-order traversal of the binary tree. So as you do the in-order traversal, write down the node IDs and the corresponding data, and leave the node IDs as it is that you got from in-order traversal. Just sort the data that you got from in-order traversal. And when you sort the data, this is a sorted order for this data, and just superimpose for node 3, instead of 22, its data is going to be 13. For node 1, instead of 27, the data is 14. So now this is a binary search tree. So you can check the root node 22 is greater than its left child, 14 less than its right child, 27. And then 14 is greater than 13, less than 18, which is less than its right child, 19, and so on. So again you see 22 is greater than everything in its left subtree. 14 is less than everything in its right subtree. So this is a binary search tree. So you can cross check. If you do an in-order traversal of this binary search tree, you're going to get these nodes listed in this order 3, 1, 4, 5, 0, 2 as well as the corresponding data. So we made use of the property that we just went through, that the in-order traversal of a binary search tree will always list the nodes in the sorted order. Okay. So I have another example here. So again, given the binary tree, we want to preserve its structure and convert that to a binary search tree. Okay. So the way we do is do an in-order traversal of this binary tree. So we all should be familiar with that by now. So when you do the in-order traversal, you list down the nodes that you visit and their corresponding data. So start with the root, don't print the root, go to its left subtree, then go to its left subtree further. We cannot go further to the left, so print the root, which is 3, and then write the data, which is 78, and then go to the right subtree, node 6, and its data 9, and then root 1, no right subtree, so then go to root 0, 34, and so on. So then once you get the in-order traversal order of the node IDs and their corresponding data, just sort the data. So the sorted order of the data is 9, 12, then 21, another 21, 23, 23, 23. So if they're duplicate data, that is okay. We can just write them like this. And then, so we are not changing the order of the nodes that we got from in-order traversal. So we're retaining that. So just superimpose. So for node 3, its data is going to be 9. For node 6, its data is going to be 12. For node 1, its data is going to be 21, and so on. So this is now a binary search tree, and you can always cross-check whether the binary search tree property is satisfied. Okay. Alright, so let me stop one more time.